Well, thank you, but I'll let you know again. My name is Rahul, and my topic for today's presentation is about how a driverless car perceives the world. So we go back to 1885. Carl Benz invents the first automobile. Later that year, he took it out for the first public test drive. And, true story, he crashed into a wall. For the last 130 years, we've been working around that least reliable part of the car, the driver. We've made the car stronger, we've added seat belts, we've added airbags, and in the last decade, we've actually started trying to make the car smarter using driver assistance systems. Well, today, I'm going to tell you about the difference between patching around the problem with driver assistance systems and actually solving the problem with having fully self-driving cars, and mainly what these cars can do and how they see the world. But first, I'm going to talk about the problem. And it's a big problem. 1.2 million people are killed on the world's roads every year. In India, 17 people are killed every hour in 45 accidents, and that makes up 408 people dying every day. And that sums up to a grand total of 150,000 people dying every year. In America alone, 33,000 people are killed every year. To put that in perspective, that's the same as a Boeing 737 falling out of the sky every single working day. And that's unbelievable. Cars are sold to us like this, but in reality, this is what driving is actually like. And the reason why is this. Traffic really is getting substantially worse than it was not very long ago. And all of this has a very human cost. So if you take the average commute time in a country like India or America, which is about 50 minutes, and you multiply it by the number of workers that we actually have, turns out that we're wasting 6 billion minutes just driving. Now that's a big number, so let's put that in perspective. We take that 6 billion minutes and we divide it by the average life expectancy of a human, which is about 37 million minutes or 70 years. Turns out that we're wasting 162 lifetimes just getting from A to B. And then, there are those of us who don't have the privilege of sitting in traffic. This is Shrikant. He's an incredibly capable person and a really good friend, but he just happens to be visually impaired or blind. Now, instead of a 30-minute drive to work in the morning, it's a 2-hour ordeal of piecing together bits and pieces of public transport or asking friends and family for a ride. He doesn't have the same privilege that you and I have. Now, shouldn't we do something about that? Now, conventional wisdom would tell me that we just take these existing driver assistance systems and we kind of push them and incrementally improve them. And over time, they'll turn into self-driving cars. Well, I'm here to tell you that that's like me saying that if I work hard on jumping every day, one day I'll be able to fly. It just doesn't work that way, and we actually need to do something a little bit different. So I'm going to talk about my journey in discovering how different these driverless systems are from driver assistance systems, and all the valuable insight that I have learned from my 3 years of research in understanding how a world is perceived by these systems. So I started off in my journey in understanding that I had to mimic a human driver. So I started asking questions that a human driver would ask every single day while driving on a very recurrent basis, such as what is around me, where is everybody moving, can I move on safely, are there limitations such as speed, and what is happening further down that road. Using this, I further dissected the entire driving process into 3 very important parts: perception, computing, and control. And I started looking for technological replacements for these parts. And then I had arrived at a complete self-driving system, a 4-part process-centered architecture, starting off with one of the most common solutions to mimicking human eyes, which was computer vision. And then moving on to localization, understanding where we are in this world around us using maps. And then charting a path from A to B, and essentially control. So we start off with computer vision. It's how we use cameras to see the world. Computers use images, and humans demonstrate the power of vision by just using 2 eyes in the brain. Computers use images to understand colors and fonts, essentially recognizing traffic signs, lane lines, and also tracking other cars on the road. And cameras have become sophisticated enough nowadays to engage in deep learning, to understand pedestrians and their behavior, which is amazing. But when you stare through the windshield of your car, you don't see the world the same way as a dash cam does. What you see is being warped by the inner workings of your brain, prioritizing detail right at the center, but also keeping peripheries to spot danger. It just doesn't happen the same way the camera does. So cameras are unreliable and they weren't perfect at mimicking humans. And they were at risk due to their range limitations. And weather limitations such as increased glare, fog, and rain increase the risk of cameras actually being wrong. And then I had come to my realization that in order for fully driverless car to prevail, we not only had to mimic, but we had to exceed the capabilities of human drivers. And that is the only way that we're going to get around this problem. So I started looking at wider applications in technology. And I understood one very sophisticated technology called LiDAR systems. Now LiDAR, short for light detection and ranging, is used everywhere in certain missile projects. And I understood that this is being put into alternative today. Now LiDAR uses lasers and light to determine the velocity and the distance of objects around the source. By using these hundreds and thousands of laser pulses generated every second, we're able to generate an intricate 3D map of the environment around you, just like what you're seeing on the screen right now. This type of technology gave driverless cars a distinct advantage over driver assistance systems. In terms of awareness levels, it was a giant leap in the right direction. Now this is what we actually wanted, but we still needed precision in terms of color recognition, and that was something that only a camera was very consistent at. Now, and this is where two of the biggest pioneering companies in driverless systems are at a tussle. One, Google saying that LiDAR is the way to go towards the future, and Tesla saying that computer vision is the way to go. I started researching and delving into basic circuitry, trying to understand and find a way to make these two sensors work together. Simply put, I wanted to understand a way in which the limitations of LiDAR could be covered by the benefits of camera and vice versa. Now, and then, throughout my research, I started understanding that that could be achieved through something called sensor fusion. Now, sensor fusion was simply software that could intelligently combine data received from all these sensors and take the most valuable data depending on the weather. So when the weather was very bad, we could rely on LiDAR, and when the weather was not, we started relying on computer vision. And LiDAR used to support computer vision. It was a very synergistic combination of both these sensors. They started working in conjunction, and that was brilliant. And then I started understanding that I had to add sensor vision into my process-centered architecture. And I also came to the conclusion that a simple multi-domain controller was enough to make these three sensors work in complete conjunction with each other, a sort of harmony, settling out in harmony. And then I also understood that with sensor fusion, I could also add other sensors and make all of them sort of come together in a conjunction and live together, which was absolutely amazing. This was a giant leap in the perfect direction. So coming back to my process-centered architecture, we start off with computer vision, followed by sensor fusion, and then maps to localize yourself, along with path planning and essential control. We're finally making the car perceive, not only see, but perceive better than a human driver could. Because to perceive actually meant to understand, to be aware. And this was what I had to achieve. We've come to the end of my journey in understanding the difference between perceiving and seeing. It was actually that simple. And then we could understand. And ladies and gentlemen, sorry. Imagine yourself watching your favorite TV show in the safe virtual hands of an autonomous data center on wheels, zipping along in the smoothly flowing traffic of one of the biggest tech disruptions of the first quarter of this century. There are challenges. Ladies and gentlemen, 90% of car crashes are caused by human error. Imagine eliminating this 90% right off the global average of 1.2 million deaths every year. There are challenges, like I described before. There are engineering challenges that I am willing to overcome in order to ultimately save lives. These lives cost us more than we could ever imagine. And those challenges might be with the algorithms themselves. Imagine how we should program a car when they come to a choice between two different competing evils. This is the trolley problem that has vexed moral philosophers and psychologists for decades. Simply put, should your car, in failure of control, hit a group of 5 school children or swerve along the side of a cliff, essentially killing you? Now, in our very utilitarian society, we would opt for maximizing the number of lives saved, except when one of those lives belongs to us or our loved ones. My 8-year-old cousin is going to be 9 years old in a month, and my job is to make sure that he never needs to get a driver's license. There's new technology here, a new vision, and these questions should be answered by every single one of you here in the audience. These questions have been vexing philosophers, moral psychologists, and engineers and technologists for ages. It is a question that should be a part of a lively and very nuanced discussion.